Now, on to DC-DC converters. Oh, true, I should start doing that. All right, cool. DC-DC converters, what is it? It's a device that takes an input voltage and produces a different output voltage. So what is it doing on our car, and where is it? Ooh, let me find. Nope, 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 not what I was trying to do. Move that onto a different screen. So I'm about to go through my photos. I have some good pictures of the DC-DC converter in... And the heatsink. It's mostly a picture of the heatsink from above. Wow, we're going back real far. Way back to last summer. There it is. Cool. Copy image, put it in the OneNote. Boom. Picture of the DC-DC converter. It's in this rusty old box that we used to call the HV enclosure. And it's got an ugly old, big, terrible heatsink on it that doesn't, I feel like it's really, really inefficient. A bit of an, what's up?
Probably.
Yeah, a bit of an aside on heat sinks. If you're designing a heat sink for anything, make it out of aluminum and put as many fins on it as possible. Because when it comes to heat transfer and heat dissipation, surface area matters, which is why you put fins on your heat sink. Anyways, what's a DC-DC converter? Yeah, so it takes an input voltage and it spits out a different output voltage. What is the principle behind DC-DC converters? If you've read about switching power supplies, then it's a very, very similar concept. So what's a link? What's a resource I can use to read about what it does? Boom, right here. This is pretty good. This website explains the difference between DC-DC or switching regulators and linear regulators. DC-DC converters are an example of a switching regulator. So what are we using a DC-DC converter for? So, well, our Tractive system is at 400 volts and our low voltage system is at 12 volts. So what we want to do is we want to take that 400 volts and convert it to 12 volts. Why, you may ask? What's the point? Shouldn't we keep our two systems separate? Well, if you know how an alternator on a car works, where it takes the, mechanical energy from an engine, rotates some magnets and some coils, and it spits out electricity so that you can charge your battery up and power all your electronics. Now, this would work similarly, where our low voltage system would run off of what's being produced by our DC-DC converter. And when we need to use our low voltage battery, we would switch over to that. So I think what it's saying is we have a low voltage battery that can be used to power a low voltage system when the high voltage system is off. Meaning you can turn one key and have all the low voltage electronics going, so you can run, check some stuff out, make sure everything's working. And it's also required by rules. You have to be able to turn on your low voltage system before your high voltage system. So that means you absolutely have to have a low voltage battery. Now, what would happen is you would turn on your low voltage system, and once you turn on your Tractive system and you're finished pre-charging and everything, then your DC-DC converter would kick in and power your low voltage system. I believe the configuration we have is that it switches between the battery and the high voltage system, instead of the high voltage system sort of just topping off the battery as we go along and running primarily off of the battery. Now, there are a few things to consider. Apart from, reading up on the difference between linear regulators and DC-DC converters. Generally, DC-DC converters are used when you want higher power output. And switching DC-DC or switching regulator can step up your output voltage, whereas linear regulators can only step down your output voltage. That's the general gist of the difference between the two. Case by case, DC-DC converters are situations where you need more power. Linear regulators are usually smaller. You use them when you want a more stable output, a cleaner output signal. So they're used for creating reference signals and stuff like that. But they're much more inefficient and they get much hotter. So, cool. DC-DC converters. I have a video linked on the More on Converters page that I thought was really, really good. It starts super basic on explaining the characteristics of inductors, and then it moves on to how switching regulators work. Yeah, so what about us? What DC-DC converter did we select? Well, we selected this Vicor, however you want to say it, DC-DC converter with an input voltage of 270 volts. That's nominal. It can go up to, I think it's 500 volts is your max. I have to double check the data sheet. And your output voltage is 12 volts. Perfect. That's exactly what we need. So, what more is there to do? Well, now that you selected your DC-DC converter, there are a few extra features. I go on a rant about heat sinks in this next section that I just highlighted. It's really not that important unless you're designing it and you've never had any experience with computers or something before. But
copper heatsink, woo.
Yep. Nope. Copper pad aluminum heatsink, because copper, what do you call it? Copper
conducts very well.
Is more thermally conductive, but aluminum actually dissipates heat better than copper. So you want to suck with the copper and blow with the aluminum. Actually, a quick aside, for the combustion cycle of combustion engines, the 4 strokes, there is a simple way of remembering it, and that's suck, squeeze, bang, blow. You've got your intake, right, where you're sucking in air and fuel, and you're throwing in air, fuel through your cans, and then you compress all of that, and then you spark, combustion, bang, and then you exhaust, which is blow. If you ever want to remember how a 4-stroke engine works, that's exactly how it goes. Yes, cool. Pin configuration. Why do we have to worry about pins if all we need to do is put our plus and minus high voltage and then our plus and minus low voltage on the input and outputs? Well, you want to be able to disable and enable your DC-DC converter. So you remember how before we calculated all the stuff with pre-charging? Well, let's say you throw a DC-DC converter that consumes 500 watts into the mix, then you're going to have issues pre-charging. You're probably not going to hit that required 95% plus 90+%, Tractive system voltage before you can flip the AARs. So then whatever limits you've set in your BMS or your inverter, they're going to end up complaining. So we need to be able to start our car with the DC-DC converter off, and then flip it on when, once pre-charging is over. How do we do that? How about reading the data sheet? So we see here that you've got a few pins that are marked out for us, and now we look at their pin descriptions to see how we use them. So in plus, in minus, out plus, out minus, pretty self-explanatory. Now, what looks interesting? Oh, EN looks like an enable pin. Now, what do we need? Needs VDDE pre-applied. Okay, cool. So we need enable and VDDE to control this. Anything else? We don't need trim. We don't need remote sense operation, and we don't need these. So now we've determined once we've selected our DC-DC converter, figured all that stuff out, we need to work with this VDDE and enable pin. So, down here is also a good note they include. All the control inputs are isolated from the primary. So they also confirm that you've got high and low voltage isolation. Right. So now that we know we're using VDDE and enable, what did I say I need to go into? Oh, right. Okay. So I should write that out. Why precharging would fail. All right. So now we know what those do. We need to figure out what voltage do we need to apply to enable or VDDE in order to get them to do what we want. So we look back at the data sheet and let's see. Enable pin. Cool. Enables and disables the DCM converter. When held low, the unit will be disabled. So we'll probably have that pin connected through a switch.
Let's step away for a second because
Yeah.
I'm getting something done. All
Sure. Right. We shall be back on it. Cool. I'll just re-explain it. So what do we need? So, okay, question for you guys. We have to deal with this enable pin. It says the enable pin, when held low, the unit will be disabled. So how are we going to control that enable pin?
Invert the low voltage system power.
All right, that's an option. Question mark. All right. Well, what I was thinking was what we did before that worked out pretty well is you can control the DC-DC converter. There's two, shoot. Okay, so let's go with the simpler option. It's controlled by a switch on the dashboard, right? So you have a wire going to the enable pin that goes to that switch, and the other end of that switch goes down to ground. So when that switch is closed, your enable pin is connected to ground, and when that switch is open, it's not. Now, that's all good and all, but is there any problem that you could think of with that sort of situation? So an issue that we can run into is if you look on the datasheet page that I've pulled up, you have your max. What's your enable threshold? Where in order to be considered enabled, it has to be above 2. What do you call it? It has to be above 2 volts, and in order to be disabled, it has to be below 1 volt. So what would we do here? Actually, now that I think about it, so you would actually want to have that switch. You have a switch on your dashboard. One end goes to enable, the other end actually goes to plus 5 volts. That would be better, right? Wait, what the hell? Ah, damn it. Okay, so you know what we got to do here? Oh, shoot. Okay. Enable internal pull-up. Oh, okay, never mind. Cool. So all our questions are answered by this datasheet page right here. So I was thinking, okay, so we need to have a pull-up resistor so that when it's left open, it's not doing jack. But they say over here that there is an internal pull-up. So what does that mean? That means that if you have your enable pin connected to ground through a switch, when it's not connected to ground, it will automatically be pulled up above the logic level, right? So it won't be floating. A lot of times you have to worry about having a floating voltage when your pin is just hanging, not connected to anything. And the good practice is to have either a pull down or pull up resistor, depending on your application. You'll see this most when you're working with Arduinos. But yeah, so enable, have it connected to ground through a switch. You can also make it automatic, where you can have it controlled by a microcontroller that communicates with the BMS, or if you're using the BMS microcontroller itself, you can have it go from You can have it tell you when pre-charging is done, then enable DC-DC converter, so unground it. So that's how we use the enable pin. We don't need to worry about trim. And the only other thing we need to do is apply VDDE, which powers the internal controller. We need to read the datasheet in order to realize that it takes 5 volts and not 12 volts. Because your max is 10 volts. So if you put 12 volts from the low voltage system, then you're probably going to fry something or damage something at the very least. Cool. So any questions on how we do enabling and that yarn? Cool. Now, I actually think this next part is the only part you really need to read from this page. Everything else you can kind of just, it's not really that hard to understand. Even this isn't really hard. But why do we even need a DC-DC converter? Well, I go more into detail than I did last time. Basically, you don't really need a DC-DC converter. We probably shouldn't have run with one because the complexity it adds is the trade-off for having a better design. Now, the biggest benefit that you get is that depending on the draw of your low voltage system, you may be taking your ability to run for like 40 minutes max. Like that's realistic. You can run your car as long as your high voltage battery lasts out. So you can control this. So you can run for like hours, which is really, really, really useful for testing. And it makes competition way less stressful because you're in a mad dash to try and get all your events done. But it complicates the design because you need to have, once you have your DC-DC converter, you need to have a circuit that switches between the low voltage battery and the DC-DC converter. And in order to house that circuit, you need an extra printed circuit board. And then you need to interface a lot of different things. You need to run a switch to the dashboard or have it communicate with the BMS. More complexity, and the more complex designs we have on our car, the less likely we are to actually get them to work properly.
Keep it simple, stupid.
Yes. Keep it simple, stupid. So that's honestly something you'd have to take up with the TAs, because the other justification is when you have 25 people in the class and you got to give them all something to do because it's a capstone project, you can't just make them do grunt work, then it's tough. And that's a case where I could see this coming into play. What would be the best of both worlds? Well, you design your system to run without a DC-DC converter, but you leave the option open. So you actually design your system to like be able to switch between either having a DC-DC converter or not, either way. For example, you leave enough room in your high voltage enclosure. Maybe you even run like a switch to the dashboard. Everything's like ready. You just need to drop it in, drop the PCB in, and you're good to go. But yeah, that would require more work as well. But it would leave you open to both options.
Which one would be more weight efficient?
Weight efficient.
How much heavier is a bigger low voltage battery going to be than our current one?
See, that depends. We'd have to measure the overall power consumption of the low voltage system with everything on. So all fans running, everything going full blast. And then you would have to see like, how would I size my low voltage battery if I didn't have to worry about that? If we were just running alone, if you wanted to go for minimum weight, simplest design, then you would be like, all right, I just need a low voltage battery that'll run this whole system for for an hour. That would make testing a pain in the ass, but it's possible. I actually do think you could save on weight then. Because if you have a DC-DC converter, you can size your battery to be smaller, but I think it would make enough of a difference. Plus, I don't think I think you should consider weight in any design report that you're doing, but in the end, you should come to the conclusion, especially with our car and our situation, of weight doesn't really matter right now.
Well,
because
I wasn't saying that's a
big
deal
but
yet. We need a working car first.
Yeah, but no, that's still something that should be looked at. Mostly, it's just the power draw of the low voltage system that you got to look at, and that's something that we should measure regardless, because that's your design justification for having either a DC-DC converter or not, and what
Preston, go
size
yell
low
at
voltage
Melissa.
battery.
Or Dylan now, actually. It's Dylan now.
I can still yell at Melissa. It's fine.
Yeah,
I
you
mean,
can still
yeah.
yell at Melissa. So that was mostly what I had on the DC-DC converter.